Welcome to the third session of Functions and Relations series. In this session, we will go through function domain and range, and other features of functions such as odd and even functions. We will solve 8 worked examples targeted to improve your competitiveness in analyzing and solving mathematical questions. Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome to the third session of this Functions and Relations series. There are 8 worked examples shown in this session, and some of them are quite challenging. I hope you will improve your competitiveness in analyzing and solving mathematical questions after watching this video. Let's first briefly review the definition of domain and range. As it can be seen, the set of all the first coordinates of the ordered pairs is called the domain, while the set of all the second coordinates of the ordered pairs is called the range. The first example shows a set A. As we can see, it contains elements of natural numbers under the condition that y is also a natural number. Y has the rule of y equals 12 over the sum of x and 3. Since both x and y are natural numbers, the possible values of x can take to make y is a natural number are 1, 3, and 9. However, it is worth to note that if the natural number begins from 0, the possible values x can take are 0, 1, 3, and 9. Example 2 shows 2 sets of A and B. Set A contains elements of natural number from 1 to 5, while set B contains elements of x and y. Given that both x and y are elements of set A and the difference of x and y is also an element in set A, the question is to find the number of elements which is a pair of x and y in set B. Now, the analysis starts from x equals 1 and then moves forward. When x equals 1, there's no value y can take. When x equals 2, y only can take the value of 1. Now, let's step up the abstraction by assuming x takes a number of n. Here, n is the number less than 6. Then y can take the number from 1 to n minus 1. Hence, we list all the possible pairs of x and y and find the total number of elements in set B is 10. Example 3 is a logarithmic function. F of ax minus 1 equals common logarithm of x plus 2 over x minus 3, where a is a non-zero real number. There are 3 questions to follow. The first one is to find the expression of fx. The second one is to find the implied domain of fx, and the last question is to discuss the relation between the parity of fx and the value of a. Here the parity means the feature of odd or even functions. As for the first question, we assume y equals ax minus 1. Hence, we can express x in terms of y. As it can be seen on the screen, x equals y plus 1 over a. The next step is to replace x by the y plus 1 over a to the original equation, and we have the expression of fy equals common logarithm of the sum of y and 2a and 1 over the sum of y negative 3a and 1, which is equivalent to fx. The second question is to find the domain of fx. Since it is a logarithmic function, the argument must be greater than 0. Therefore, we have two pairs of simultaneous inequalities to sort out the domain of fx. In order to have the argument greater than 0, both numerator and denominator must be greater than 0 or less than 0 at the same time. In the meantime, we also find out the critical point of a equals 0, and based on that, we discuss the implied domain of fx. Hence, we find when a is less than 0, x is greater than negative 2a minus 1 or less than 3a minus 1. When a is greater than 0, x is greater than 3a minus 1 or less than negative 2a minus 1. Here we continue on question 3 of example 3. To discuss the parity of fx, we need to recall one important feature of logarithmic function, which is a logarithm of fx equals the negative logarithm of the reciprocal of fx. In this way, we may check if fx is symmetric about original point or symmetric about the y-axis. In order to check if fx is symmetric about original point, we assume f negative x equals negative fx. After simplifying the equation, we find that a equals 0 or 2. In order to check if fx is symmetric about y-axis, we assume f negative x equals fx and then try to find the value of a. After solving the equation, the value of a is obtained, which is 0, according to the given criterion that a is not allowed to be 0. Therefore, when a equals 2, fx equals the quotient of x plus 5 by x minus 5, which is an odd function in this case. Otherwise, fx is neither odd nor even function. In example 4, the function is a piecewise function fx which takes a different rule over different subsets of its domain. The question is to find the real value range of a given that fa is greater than a. Since fx is a piecewise function, we have to start with the discussion of the value range of a. Now, when a is greater than or equal to 0, fa minus a equals negative half a minus 1, which is greater than 0. Hence, we solve the inequality and find that a is less than negative 2, which is a contradict to the assumption that a is greater than or equal to 0. So there's no solution when a is greater than or equal to 0. However, when a is less than 0, if a minus a equals 1 over a minus a, which is greater than 0. After solving the inequality, the value range of a is obtained, which is less than negative 1. Example 5 is a function satisfying f of half plus x plus f of half minus x equals 2. The question is to evaluate the expression of f1a plus f2a plus all the way up to f7a. Based on the given equation, and we set the value of x to 0 first, hence we have found f half plus f half equals 2. So f half equals 1. In the similar manner, we set x to the values of 1a, 2a, and 3a accordingly, and hence find that f5a plus f3a equals 2, f6a plus f2a equals 2, and f7a plus f1a equals 2. Therefore, the value of the total sum of f1a, f2a, and all the way up to f7a equals 2 plus 2 plus 2 plus 1, which equals 7. Example 6 is to evaluate a long algebra expression which involves the value of f1, f2, f3 up to f8. It is given that f of a plus b equals fa multiplies fb, and particularly f1 equals 2. Since f1 equals 2, then f2 equals f1 plus 1 equals f1 times f1, which equals 4. In the similar manner, we can work out the values of f3, f4, f5, etc. up to f8. Hence, we substitute all the values of f1, f2, etc. all the way up to f8 into the long algebra expression and obtain the result, which is 16. Example 7 has two related functions. fx equals 2x plus 3, while g of x plus 2 equals fx. The question is to find the expression of gx. Since fx equals g of x plus 2, which equals 2x plus 3, here the expression of 2x plus 3 can be changed to 2 times x plus 2, or in parentheses minus 1. Therefore, g of x plus 2 equals 2 times x plus 2, or in parentheses minus 1, which is equivalent to gx equals 2x minus 1. Alternatively, we may assume another variable y, which equals x plus 2. Then gy equals 2 times y minus 2, or in parentheses plus 3, which equals 2y minus 1. So gx equals 2x minus 1. Example 8 is to find the expression of fx given that f of 1 minus x over 1 plus x equals 1 minus x squared over 1 plus x squared. When encounter this kind of question, we need to assume the expression function variable to another variable. Here we introduce y and make it equals 1 minus x over 1 plus x. From that equation, we can find the expression of x in terms of y. And here we find x equals 1 minus y over 1 plus y. Hence, f of 1 minus x over 1 plus x becomes fy. And as for the expression of 1 minus x squared over 1 plus x squared, we can substitute x by y and then simplify it. Finally, we obtain fy equals 2y over the sum of 1 and y squared, which is equivalent to fx equals 2x over the sum of 1 and x squared. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.